Hello everyone. In this video, we're going to be taking a look at the tangent line. So what we want to find is the tangent line to the graph of some function at a given point. So the way that I want to approach this is we'll start by looking at a sketch of a graph, and we'll look at the tangent line, and we'll talk about how we can find the slope of that tangent line. After we do that, we'll take a look at a more specific example to help us reason through this. So let's start off with a simple sketch. So I have some axes here, and I just want to consider some function. Now it doesn't matter what this function looks like, so we'll just put some nice curve on our graph. And what I want to find is I want to find the tangent line at some point. So let's say we pick out some value of c. And then on our graph, on our function, we have this point here. Well, let's say we want to find the tangent line at that point. So let's give this point a name. We'll call this point P. And the coordinates of this point, so its x value is at C. And then the y value is the function value at C. Okay. Now the tangent line, it only intersects the graph at exactly one point. So if I were to graph the tangent line, it would look something like this. So it's going to bump up right next to our graph, but it's only going to intersect at that point P. Now, if I want to find the equation of this tangent line, I need two parts. We know that we need a y-intercept, and we also need a slope to define a line. Well, the way it stands right now, I can't find that slope because in order to find slope, I need 2 points, but I only have one point that's on that line. I only know point P. So this is where calculus comes in. So the way that we want to consider this is we're going to pick out a second point somewhere on our function. So we'll pick out this point here and let's call this one Q. And then let's say that this is at x. So that means that the coordinates of this point are x and f of x. If I connect together these 2 points, I get what is called a secant line. So that line that goes through P and Q, that is a secant line. And here we have 2 points, and I could definitely find the slope of that line. So the slope of a secant line, I'm going to notate this as m for slope, and then I'll put secant. Well, the slope is just you subtract the y values, and you divide that by, you subtract the x values. So here I'm going to do f of x minus f of c. Those are our two y values, and then we'll divide by our two x values, so x minus c. So that would give me the slope of the secant line. And then from there, we could use one of the points, and then we could find the equation of that. But again, I'm looking for the equation of this tangent line. So what I want to do is I want to take this point x, this value here, and I want to move this closer and closer and closer to this value of c. So what's going to happen is my point Q, I'm going to move that point Q along this function until it gets closer and closer. Okay? And as you can see, if I compare these lines to the tangent line that I drew in earlier, this line is getting closer to matching up with that tangent line. So let me switch to a piece of dynamic graphing software. So here I have a function. And what I'm looking at, I got my 2 points. And let me connect these points together with a line. So this line here is a secant line. And in order to find the tangent line, say at point P, what I want to do is take this point Q, and I want to move it closer and closer and closer to P. And as you can see, as I slide this closer, this is getting closer to being a tangent line. And if I can imagine this, if I can move Q right on top of point P, Well, now this line only intersects at exactly one point, and we end up with a tangent line. So going back to our picture here, what we want is I want to take this value of x and I want to move it closer to c. Another way I can say that is the limit as x approaches c. So to find the slope of our tangent line, so say the slope of the tangent line, instead of just our slope formula, now we're going to be looking at the limit as x approaches c of that slope formula. Okay, so using this idea of limits, we're starting with 2 points. Having 2 points allows us to find the slope of a secant line, but we want to take those 2 points and we want to move them closer together so that our limit is at 1 point, and then we have our tangent line. Another way that we can notate this is with prime notation. So if I do f prime, so a little apostrophe, we call that prime. F prime of c is the limit as x approaches c of this slope formula. So this allows us to find the slope of the tangent line. And then once we know that slope, we can use that to write the equation. So now that we understand where this comes from, let's use that in a specific example. So I have a function f of x is equal to x cubed minus 1. And then let's find the tangent line at the value c equals 1. So just as a reminder here, I'll write down our formula. So f prime of c is equal to the limit as x approaches c of f of x minus f of c divided by x minus c. Okay, so I want to find the equation of the tangent line. So the first thing I need to do is find the slope using our formula that we just found. So let's see here. I'm going to find f of c first, just so we know what we're working with. So we're going to find f of 1. That's 1 cubed minus 1, and that turns out to be 0. So that works out. So now taking a look, so our f prime of 1, this is going to give us our slope of the tangent line. We have the limit as x approaches c, which is 1. And then we're going to do f of x minus f of c over x minus c. And now we can plug in everything else that we know. So the limit as x approaches 1. So f of x is our original function. So x cubed minus 1. We already found f of c to be 0. And then in the denominator, we have x, and then our value for c is 1. Simplifying this one more time as x approaches 1, so that 0 doesn't do anything, so we just have x cubed minus 1 over x minus 1. And this is the limit that we need to evaluate. So taking a look, we can't just substitute in 1. If we substitute in 1, we'll end up with an indeterminate form, 0 over 0. So let's try and simplify our expression. In the numerator, this is the difference of perfect cubes. And that is something that we can factor. So we have the limit as x approaches 1. And if I factor that, it's going to be x minus 1, and then x squared plus x plus 1. And this is still all over x minus 1. In the factored form, we can see we have a term here that will simplify. And then what we're left with, and I'll move it up here. So now we have f of 1, f prime of 1 is equal to the limits as x approaches 1 of x squared plus x plus 1. And now we can just plug in 1 to find this limit. So the slope of our tangent line, 1 squared plus 1 plus 1, which gives me a result of 3. And that's a slope of our tangent line. So the slope of the tangent line is 3. Okay, now that we know the slope, we can write the equation of this line. So I have the slope. The other thing I need is a point. Well, at this value for c of 1, if I plug that in, I end up with the point 1, 0. So now using those two things, the slope and that point, we can write the equation of this tangent line. So I like to do this in point slope form. So that looks like y minus, and our y value is the function value at c. And then this is going to be equal to the slope of our tangent line times x minus our x value for our point, which is c. So plugging in what we know, we have y, our function value at c is 0. Slope of our tangent line is 3 times x minus 1. And simplifying this, we get y is equal to 3x minus 3. And there's the equation of the tangent line at that specific value for c. And to just verify and see what this looks like, let's go back to our graphing software and graph both of these things and see what this looks like. So here we have our original function. So this is the graph of x cubed minus 1. And then let's put in our line. So the line 3x minus 3. So here's that line. And as you can see, it intersects the graph at exactly 1 point at the point 1, 0. So it is tangent at that point.